Hello, everyone. How are you? Fine. Today, we are going to talk about superfluid, that is liquid helium. Liquid helium features very interesting properties, and that we are going to discuss in this particular talk. And they are exhibiting superfluid nature. So let me share the first slide regarding the liquid helium. And uh, this first slide first defines that what is superfluid. A superfluid is a liquid that flows without dissipation. The classical example is liquid helium-4 in its low temperature phase, and which can flow through the tiniest cracks without viscosity. So it does not exhibit any viscosity. And that is similar to superconductivity, which we experience in electrical conductors. So where the charge carriers are Cooper pairs. So superconductivity and superfluid nature both are similar natures. First question is why helium does not solidify. So there are many problems related to why helium does not solidify. Helium is the only substance known to resist solidification under atmospheric pressure down to the lowest temperatures observed, maybe up to absolute zero. So up to absolute zero, if you cool it down, it does not solidify. To solidify, it requires an external pressure at least up to 25 atmospheric pressure. So if you want to solidify liquid helium, then you have to apply a pressure and also reduce the temperature. So both the things are required to solidify helium. This is giving two naturally occurring quantum liquids. One is helium-4 and less abundant isotope is helium-3. The quantitative reason for fluidity of helium are discussed like this. First reason is the molecular interactions between helium atoms are weak, as this is a noble gas. So helium gas atoms, they have a very less interaction being a noble gas. And the mass of helium is the smallest among all the noble gas atoms or noble gases. So these are the two important reasons why helium is not getting solidified. There are circumstances lead to large zero-point motion of the helium atom, and so that it becomes impossible to localize atoms at well-defined lattice sites. We know that in harmonic oscillator theory, the zero-point motion are already discussed. So zero-point motions means zero-point energy. That is when the atoms are cooled down up to absolute zero temperature, then zero-point motions are still remaining, and that motion is quite high. And that is not possible to localize at well-defined lattice sites. We have a drawing of a potential energy diagram. The potential energy VR between two helium atoms separated by a distance r has been calculated by Slater and Kirkwood on the basis of electronic structure of helium atom. So this is the calculations they have done, the potential energy between two helium atoms, and that is shown in a figure in the right-hand side. It is given as VR 5.67 10 to the power 6 e to the power minus 2.5 into r divided by sigma minus 1.08 r divided by sigma raised to 6. One has to be very careful over here. In this formulation, 6 and sigma both are incorporated. So we have to be very careful to distinguish a difference between sigma and 6, where sigma is 4.64 angstrom and VR is represented in Kelvin. So the potential energy diagram is shown in a Kelvin, and we know that average energy can be related to 3.3 by 2 kT, and the potential energy and the kinetic energy are considered to be the part of energy. So from these formulations, potential energy equal to kinetic energy equal to 3 by 2 kT. From there, we can find out the depth of potential well in terms of Boltzmann constant. So this can be calculated very easily, or this can be calculated in terms of the Kelvin also. So potential energy is equal to 3 by 2 kT. And in that case, we can use temperature to represent the potential well depth, or we can use the Boltzmann constant to represent the potential depth. Both are possible. From the slope of dP, means pressure, by dt, the absolute temperature of experimental vapor pressure curve, one can find the latent heat of vaporization for liquid helium. The extrapolation of experimental data up to absolute zero indicates that dP by dt is greater than zero at absolute zero. And therefore, the liquid helium has non-vanishing, means non-zero, binding energy per atom at absolute zero. And therefore, that is the ground state that has a self-determined equilibrium density in absence of external pressure. So that is represented in a figure. And the potential well depth is represented as minus 9K. And on y-axis is the potential energy, on x-axis a distance. Now we consider a collection of helium atoms at absolute zero under no external pressure. So we are not giving any external pressure. The most probable configuration of atoms is determined by the ground state wave function. And we know that how to calculate the ground state wave function using the harmonic oscillator model. This ground state wave function, which is according to the variational principle, must be such that to minimize the total energy of the system with no external constraint imposed. And we also know that the variational method in quantum mechanics is used to determine or confirm the ground state wave function or ground state energy of a system. So first we can calculate the ground state wave function, and from that we can calculate the ground state energy, or we can confirm by variational principle. Applying the variational principle, we can confirm the ground state energy value. Hence, the energy consideration alone determines the most probable configuration. If a helium atom to have a well-defined location, it must be confined to within distance of delta x, that is small compared to the range of potential. So range of potential is approximately of 0.5 angstrom. So if helium atoms to have a well-defined location must be within the 0.5 angstrom of distance, or delta x 0.5 angstrom. By the uncertainty principle, we are applying here uncertainty principle, one can expect an uncertainty in the energy in units of Boltzmann. We have already discussed that energy, average energy or average kinetic energy can be equated to average potential energy, and that is 3 by 2 kT. K is a Boltzmann constant. So energy can be represented in terms of Boltzmann also. So in units of Boltzmann, and that can be represented as delta E approximately of order of 1 by 2 m h cut divided by delta x square, and that is of 10 K. Now this is comparable to the depth of potential well. So let us go back to the figure. Here we have a depth of potential well is minus K. So the energy we have obtained from uncertainty principle is 10 K. It is of the order of the potential or potential well. So therefore, the localization of atom is impossible. And also, therefore, they do not form a lattice to make a solid substance. To make a solid substance, the localization of atom is must, or it is the requirement. And they must remain within the potential well. If they do not remain within the potential well, they jump out. They don't form a lattice. And if they don't form a lattice, their solidification is not possible. So it is similar to say that the highly dynamic monkeys are difficult to sit in chairs at the same time. It is very difficult that monkeys can sit in chairs at the same time. They easily jump out, and they do not form a disciplined audience in a hall. So the fact that no other noble element can remain in liquid form down to very low temperatures is due to their much greater masses. So other noble gases, they remain in a liquid form uh, uh, because of their higher masses. However, the hydrogen gas, which is H2, is lighter than helium, but it solidifies at a finite temperature, is explained by the strong molecular interaction between H2 molecules. So H2 molecules have a strong interaction between them, and because of the strong interaction, they remain confined, and the solidification of hydrogen is possible, even though hydrogen is lighter than helium. This is depicted in a very interesting manner. We have found that one day in one school in Jabalpur, the window was open and monkey entered into the principal's chamber, and accidentally monkey, by curiosity, occupied the chair of principal. But being highly dynamic, it did not sit for a much time, and it stood up and jumped out of the chair of a principal. So it is shown in a figure. So very difficult to make a monkey sit on a chair for a long time before jumps out. Similarly, helium atoms cannot be confined to a potential, as their energies are comparable to the confining potential well, and they come out immediately. So we have seen in the diagram, the potential well depth is minus 9K, and energy is of order of 10K. So energy is almost of the order of potential well depth. So it is very difficult to confine the helium atom within the potential well. So that is depicted in a picture by giving example of a monkey sitting on a chair. Now, another important part is the lambda transition. So liquid helium phase has a second order, or that is the known first order phase transformation, dividing the liquid further into two parts. So that is helium-1 and helium-2. The former, means helium-1, is the normal type of liquid, but the helium-2 exhibits superfluid behavior. And that is depicted in a phase diagram. The first diagram on the left-hand side shows the solid liquid part is divided into liquid helium-2 and liquid helium-1 part, and the gas part is also shown. So there are three phases. So gas phase, solid phase, and liquid phase. Liquid phase is again divided into two parts. One is liquid helium-2 and liquid helium-1. And that forms a phase diagram that is depicted by a lambda shape. It is having a shape of lambda, and that is why it is known as a lambda transition. So this is the transition line is shown, and in the transition line divides the liquid into two parts, liquid helium-2 and liquid helium-1. And that is occurring at the temperature of 2.18 Kelvin. And that is also a critical point is shown in the phase diagram. And the solidification is occurring at 25 atmospheric pressure. And if you apply more than 25 atmospheric pressure, the liquid helium solidifies. So solid phase, liquid phase, and gaseous phase. And the critical point is shown. Now, this is called as a lambda transition because it is having a shape of lambda, that is a Greek letter. Although the vapor pressure curve, it occurs at the temperature T lambda and a specific volume V lambda. So T lambda is 2.13 Kelvin and V lambda is 46.2 angstrom by atom. So another diagram is shown that is a three-dimensional picture. The pressure, then the volume, and temperature, all the three are shown. And that is a odd-looking or crude-looking diagram because all the three phases are shown. So solid phase, liquid helium-1, liquid helium-2, and gas phase. So that is shown in a three-dimensional phase diagram. Now, the specific heat along the vapor curve becomes logarithmically infinite as the point of Lambda transition is approached from the both sides. So if we approach to the Lambda transition from both sides, means from absolute zero or from higher temperature. So the specific heat approaches to infinite or approaches to infinite value. And that is shown in a diagram on the right-hand side. So specific heat is shown on the y-axis, and the temperature is shown on the x-axis. At the lambda transition, T lambda, it approaches to infinite value. It is significant that helium-4 exhibits the lambda transition and helium-3 does not. Apart from the difference in atomic masses, the only difference between these two substances is that helium-4 atoms are bosons and helium-3 atoms are fermions. So this is the main difference. Here it is assumed that the lambda transition is the Bose-Einstein condensation modified by molecular interactions. So we can correlate to Bose-Einstein condensation. In fact, an ideal Bose gas with the same mass and density as liquid helium-4 would undergo Bose-Einstein condensation at 3.4 degree Kelvin, which is of the order of the magnitude of T lambda. So that proves that it is behaving like a Bose-Einstein condensation. The isotope helium-3 undergoes a phase transition to a superfluid phase at much lower temperature of 10 to the power minus 3 Kelvin. And the physical mechanism is similar to the superconductivity, in which the bound states or bound fermion pairs form the condensate. Here we want to briefly mention about the Bose-Einstein condensation. So Bose-Einstein condensate, or BEC, a state of matter in which the separate atoms or subatomic particles cool down to near absolute zero temperature, coalesce into single quantum mechanical entity, that is, one that can be described by a wave function or near macroscopic scale. So it works as a single entity. Now, another important part is the Tisza's two-fluid model. That is a very interesting part related to liquid helium. When Kamerlingh owns first liquefied helium in 1908, some unusual properties of this liquid below 2.18 Kelvin was marked. It was found that the liquid helium will crawl up the wall of a container and coat the inside surfaces unless the part of the container is above T lambda temperature. If you place it in an open beaker, the liquid will crawl up the wall, cross the rim, and will flow out of the beaker. Really surprising. And that is why it is called as a superfluid. In the right-hand side diagram, it is shown that the container which is having a liquid helium is kept and the temperature is maintained in such a way that it crawls out of the container and drops on the floor. So that is shown in the diagram. Tisza postulated that the phase of helium-2 is made up of two components called the normal fluid and superfluid. So liquid helium is postulated to have two components. One is normal fluid and superfluid. The phase 1 is the nominal fluid. Some unusual features can be described in terms of phenomenological model proposed by Tisza, known as Tisza's two-fluid model. Considering mass densities rho n and rho s, that is for the normal fluid and superfluid, to normal fluid and superfluid, and characteristic velocity fields are V and Vs, again representing the normal fluid and superfluid. So the mass density and velocity fields of helium-2 are assumed by rho equal to rho n plus rho s. And the total rho into V can be represented as rho n Vn plus rho s Vs. The normal fluid behaves like a classical fluid, but the superfluid behaves in a different manner. So its entropy is zero. Superfluid entropy is zero. Superfluid can flow with no resistance through channels of extremely small diameters. So diameters are 10 to the power minus 2 millimeter or less than that. So it can pass very easily through very narrow channels, and it does not have any entropy. An extremely small opening in a tank of liquid helium-2 acts as a filter for superfluid component, because superfluid can pass through the opening and leaving normal fluid behind. So suppose we are having a liquid helium-2, which is made up of two components. One is the superfluid, another is normal fluid. Superfluid can pass through the narrow channel or a narrow opening, and normal fluid cannot pass through that. So by that, one can separate out superfluid and normal fluid. Now we discuss a very interesting experiment that is known as a mechano-caloric effect. Now this experiment is shown in which the on the right hand side the diagram is shown. We are taking two closed containers, and they are filled with liquid helium-2. And through a piston, we can apply a pressure. So piston P1 applying pressure on tank A, piston P2 is applying pressure on tank B. And there is a small channel or a small tube, which is extremely small. The diameter may be less than 10 to the power minus 2 mm, and that is connecting the two containers. So by applying a pressure on tank A, higher pressure than on tank 2 or tank B. So pressure of tank A is higher than tank B. So that allows or that forces the liquid to pass through the channel. And that is forcing the liquid to flow through the channel. So that is shown by an arrow. So what happens that the tube is very small. The diameter is 10 to the power minus 2 mm or less than that. So only superfluid can pass through, but normal fluid cannot pass through. So that is why the more and more amount of normal fluid will remain in tank A, and more amount of superfluid will pass from the channel, and it will pass from tank A to tank B. So that is described in this diagram. Now, what is the effect of this experiment? So more amount of fluid will pass, superfluid will pass from tank A to tank B. So tank A will warm up and tank B will cool down. Why tank A will warm up? Because large amount of normal fluid will remain there, and normal fluid will have higher entropy, because normal fluid is behaving like a normal fluid. So entropy increases in tank A as large amount of superfluid flows out from tank A to tank B. In tank B, large amount of superfluid comes in, and that is why the entropy decreases, because superfluid does not exhibit entropy, and temperature of tank B cools down, and that is shown over here. T1, temperature of tank A, is higher than temperature of tank B, that is T2. So this is known as a mechanocaloric effect. The reverse or inverse of the mechanocaloric effect is where we create a creation of pressure difference by heating, that is known as a fountain effect. So the inverse effect of mechanocaloric effect is fountain effect, where the creation of pressure difference is done by heating, and the diagram is showing the fountain effect. So fountain effect is exactly inverse effect of mechanocaloric effect. Now we come to another important part, interesting part, and that is known as a second sound. In the two-fluid model, which was proposed by Tisza, a wave in helium-2 is considered as a sinusoidal oscillations of rho n and rho s in phase with each other. So in the figure in the bottom, the first figure shows the normal sound, where rho n and rho s, they vibrate in a sinusoidal manner in phase. And because they vibrate in phase, the total mass density varies sinusoidally, because both the phases are vibrating or oscillating in phase. And that is why the mass density vary sinusoidally. Both mass density, rho n and rho s, vary sinusoidally, or they change sinusoidally. And that is shown as a high amplitude wave in the diagram in the bottom. That is described by a first sound. Now one can imagine a new mode of oscillations in which the normal fluid and superfluid, they oscillate out of phase by 180 degree. In the first case we have described, they oscillate in phase. Here we imagine that the sound where the oscillations are taking place out of phase by 180 degree. This would be a sound wave for which the total mass density would be constant, because rho n and rho s, they oscillate out of phase, and that is why the mass density change will be constant. There is no oscillation in mass density, and therefore the mass density will remain constant throughout the liquid. But it would represent a sinusoidal variation in entropy per unit mass, because the superfluid has no entropy, though the mass density oscillations are not taking place. But superfluid has no entropy and normal fluid has entropy, and that is why the variation in entropy is taking place. Therefore, one can excite this new mode of oscillation by local heating of helium-2. The temperature gradient is established, would not propagate by diffusion, as it occurs in normal heat conduction, but it propagates like a wave with characteristic velocity. And this phenomenon is known as a second sound. This phenomenon is described in the diagram. In the diagram, the first part shows the normal sound, and the second part shows the second sound, where rho n and rho s oscillate out of phase. In the first figure, they oscillate in phase, and that is why the amplitude is large of a sine wave. But in the second figure, they oscillate out of phase, and that is why their oscillations are not large, and that is described in the second figure. And this is a very interesting phenomenon which is called as a second sound. Now we come to one more interesting experiment. The problem is we have imagined that helium-2 is composed of normal fluid and superfluid. It's a mixture of the two. But how one can decide the amount of normal fluid and superfluid? In a particular fluid, what will be the amount of superfluid? What will be the amount of normal fluid within helium-2? How to decide or how to estimate it? The experiment is very simple. It is something like a stirring. And at home, we prepare or we stir buttermilk to extract butter. So the same experiment is done over here. Just stir the liquid as we stir buttermilk at our home to extract butter. So in two-fluid model, the relative amount of normal fluid and superfluid present may be found out by an experiment proposed by Andronikashvili. In this experiment, though looking very simple, in the right-hand side figure, it is shown that a container is having a liquid helium-2, and one shaft is there, it can rotate. And then that shaft, we have placed a disc, and discs are placed very close with each other. So they are put apart 0.2 millimeter distance. So disks are kept at the distance of 0.2 millimeter. So distance between the two disks is very small, that is 0.2 millimeter. So pile of disks placed 0.2 millimeter apart are mounted on a shaft. And this is made to rotate in helium-2. The amount of inertia of the assembly is measured as a function of temperature, where helium-2 in equilibrium with its own vapor. By assuming that the superfluid remains completely unaffected by rotation of disk, whereas the normal fluid between the disk is dragged in rotation, and hence the amount of inertia must be proportional to rho n divided by rho, because there is no viscosity experienced by superfluid, but viscosity experienced by normal fluid, and that is why the dragging is experienced due to normal fluid, but no dragging is experienced due to superfluid. The proportionality constant is determined by the fact that at the transition temperature, rho n divided by rho is equal to 1. So at Lambda transition, the amount is same, and that is why rho n divided by rho is equal to 1. And the equation is like that: rho n divided by rho equal to T divided by T lambda raised to 5.6. And that is for temperature below the T lambda temperature, the transition temperature. And rho n divided by rho is equal to 1. It is at T lambda temperature or greater than T lambda temperature. So this experiment is very simple, but very interesting experiment to determine the relative amount of normal fluid and superfluid in liquid helium-2. Now we come to the contributors. The H. Kamerlingh Onnes, born in 1853, passed away in 1926, Dutch physicist and Nobel Prize winner, first liquefied liquid helium and discovered superconductivity. Another scientist is Laszlo Tisza, born in 1907, passed away in 2009, Hungarian physicist. And John Gamble Kirkwood, born in 1907, passed away in 1959, American physical chemist or physical chemist. And last one is E. Andronikashvili, born in 1910, passed away in 1989, Georgian physicist. They have given a contribution in understanding superfluid. And thank you very much. Thank you very much for patient hearing. Thank you very much.